Hello everyone. Today we're going to be solving number 30 on 2023 chapter sprint round. So the question reads, consider the 6 points on the circle shown below. If George draws line segments connecting pairs of points so that each point is connected to exactly 2 other points, what is the probability that the resulting figure is a convex hexagon? Express your answer as a common fraction. Okay, so for it to be a convex hexagon, well, a convex hexagon basically has 6 sides such that its angles are less than 180 degrees. And also, one thing about a polygon is that its sides never intersect over each other. So, for example, this is not a polygon because there's an intersection here. They overlap over each other, essentially. And this isn't a polygon either. And it always must be closed. So you can't just call this a polygon. You need this to be closed. Okay, so keeping that in mind, we're going to look at this diagram. And the thing is, you see that there's only one way to make a convex hexagon. That is, you need this, so I'm going to call this point A, B, C, D, E, F. So you need point A to be connected to point B, B to be connected to point C, C to be connected to point D, D to be connected to point E, and E to be connected to point F, and finally A to be connected to point F. Any other configuration, if you test it out, you'll see will not give you a convex hexagon because either the lines will intersect or it won't have 6 sides. Or like angles won't work either. Okay, so only one way. A convex hexagon. Now the question asks, what is the probability that the resulting figure is a convex hexagon? So probability of something is the number of desired outcomes, or like what you're trying to achieve. Out of the number of total outcomes, or all the possible ways you could have this thing satisfied. So how would we calculate that? Well, let's start with point A. How many ways are there to connect, let's see, how many ways are there to connect A to 2 other points? Well, I'm gonna make this case 1, because there might be like, we might come up with something that is a restriction that we have to consider like 2 possibilities of. So A can be connected, oops, no, case 1 comes after, sorry. A can be connected in, well, you have 1, 2, 3, 4, 5 other points, so 5 choose 2 ways because it doesn't matter which order you connect them in, so this gives you 10. And now suppose point A is connected to, let's say, B and E, right? Or let's say actually B and F, that'd be nice. Now, how could the rest of the connections be made? Well, you have one case where B and F get connected to each other. So B and F already have one connection. They're both connected to A. So now they just need one more connection per point. So B and F connection, in that case, if B and F get connected, well then C, E, D must be connected to each other too, right? Because otherwise you won't be able to satisfy the each point is connected to exactly 2 other points, and C, E, and D cannot be connected to A, B, or F because they're already taken twice. There's one way of doing that. Okay, but what if B and F are not connected? In that case, B can be connected to C, E, or D. Oh, but then F could also be connected to C, or E, or D, and you don't know if they're sharing the point they're connected with. So that's going to be a new case. So here I'm going to list what we have for our cases. So case 1, B and F connected. And notice that we're going to have to multiply everything by 10 at the end, because regardless of these cases, A can always be connected in 10 ways. So I'm going to say one way here. And now we're going to analyze case 2 a little bit deeper. So case 2, B and F are not connected. It could be literally any pair of points. It doesn't have to be B and F, but I'm using B and F so we can actually visualize this. B and F not connected. So you have part A, which is connect to same point. And I'm actually going to draw it on this. So once I erase this hexagon. So you have, suppose A and B are connected and F are connected. Suppose they both connect to point C, right? Can this work? Well, you see, A, B, C, and F have satisfied that they're connected to exactly 2 other points. But E and D can't do that, because E and D can only be connected to each other now, because if they connect to A, B, C, or F, those are already done. So you're just going to end up having them be connected to 3 other points, and that's not what you want. And E and F are just left alone. So this gives you 0 ways, because you just can't do this. You're not going to have... E and F are going to be lonely. Sorry, E and D. Okay, so they can't be connected to the same point. Well, that means they must be connected to different points. So be different points. So you have, well, 3 ways of choosing what B is connected to, times 2 ways of choosing what F is connected to, because F can't be connected to what B is connected to. So let's say F gets connected to E. That gives you different points, 6 ways. And then from there, you see C and E have to connect to D. In this specific example, by the way, this is not always the case. It depends on where everything ends up. So like A could have been connected to C and E in the beginning, and you would not have gotten this hexagon. So okay, case 2 gives you 6 ways. So total, we have one desired outcome out of, remember we have to multiply the total outcomes by 10. It's 10 times 1 plus 6, because only after it's connected do we have these cases. So this gives you 1 out of 70. So the probability that the resulting figure is a convex hexagon is 1 out of 70, and we are done.